Okay, Assalamualaikum and salam sejahtera. This is tutorial 4.1, the first tutorial of topic 4, DC machinery fundamental. Okay, so we have already learned DC machinery fundamental in our topic 4, and then we have already finished. Then this is the first tutorial that I'm going to talk about on how we can solve the problem from example 7.1 here. All right, so we have this example here. Let me just read this question first. Example 7-1 that represents the tutorial 4.1 for this particular session. Okay, the figure shows a simple rotating loop, okay, which is this figure that shows the simple rotating loop between the curved pole faces connected to a battery and a resistor through a switch. So we have this wire loop, okay, inside the curved pole faces, and then we have the battery connected to the terminal that coming from the brush. Right, we have the commutator here for the DC machine, then we have the battery and then the resistor. All right, the resistor shown models that the resistor shown models the total resistance of the battery and the wire in the machine. The physical dimensions of the characteristics of this machine are B equals to 0.25, R equals to 0.5, L equals to 1, VB is 120, and R is 0.3. So all of the values are given here. So I have redrawn this particular question. Okay, but this example I've redrawn it here in my canvas here, as you can see, and all of the values given here is with no unit. All right, so we have this battery connected to the resistor, and then through that brush the current will be flowing to the wire loop inside the curved pole faces here, and then go back to the battery. All right, so once this wire loop is supplied by the current, we can use FILB, which is using our right hand rule. We can determine the direction of the force, which is the direction of the torque. That means as you can see here, the direction of the torque for that particular segment, I mean for example, let's say this is the CD segment. Okay, let's say this is the CD segment. Okay, for this segment the torque is to the downward direction. For the other segment, AB segment here, the torque is to the upward direction, meaning that this particular wire loop will be rotating counterclockwise direction. Okay, so the rotation of this wire loop is to the counterclockwise direction. That is the thing that we want to understand from this particular example. So we just focus on the first question: what happened when the switch is closed? Let's say we have the battery here. This particular switch is still open. Then we at t equals to 0, let's say that we close this switch to allow the current flowing to this resistor go through the wire loop. Okay, the current will be flowing inside the wire loop. Okay, what happened is the torque will be induced lah. That means that this machine is working as a motor, which is this machine. Okay, let me just write down the question A. Okay, what happened when the switch is closed? So the answer is, if a switch is closed, current will be flowing. Current will flow in the loop since the loop is initially stationary. That means at that time the induced voltage is basically still 0. So in that case, current I is VB minus E in. So this particular equation we can find in our lecture notes. You can find this in your lecture notes. I think in the previous lecture notes. In the previous lecture notes. So basically we can, if this machine is working as a motor, initially this machine, we know that in that particular instant of switch is turned on, okay, VB is larger than the E in. In that particular instant, we know that this induced voltage is still 0. Okay, so in that case, induced voltage is still 0. So we use that equation. Okay, we use actually I have used the equation from VB equals to E in plus IR. Okay, so I rearrange this to estimate, to calculate the current. So VB minus E in divided by R. So in that instant, we know that at t equals to 0, when we close the switch, induced voltage is 0, meaning that we can calculate current as VB divided by R. Okay. Okay. So that is what happened at the instant of when we close the switch. All right. So next, we know that current is VB divided by R. Okay. What happened next is this current flows through the rotor. This is the wire loop, producing torque. Okay, so this current, when we switch on, current will be flowing. That current is VV divided by R. That current will be flowing through this wire loop, and this wire loop is inside the magnetic field. So what happened is it will induce the torque, then the wire loop or rotor will start to rotate. Okay, we can describe it like that, which is the torque produced now is torque induced is 2 over pi phi I. Okay, then and this torque is counterclockwise direction. As you can see here clearly, this torque is counterclockwise direction. All right, so we can also continue to write that this torque produce an angular acceleration of omega m, angular velocity, sorry, omega m, just okay, in counterclockwise direction, in CCW. So the rotor begins to turn. Okay, so the rotor begins to turn. all right, to turn counterclockwise direction. Then once the rotor turns, revolve, all right, okay, what happened next? Okay, we can say that, but as the rotor begins to turn, an induced voltage is produced. An induced voltage is produced. When the rotor starts to revolve, the induced voltage will be produced in the motor. That is given by, so the formula of induced voltage is E in 2 over pi phi omega. Okay, omega m is mechanical torque. Okay, mechanical velocity. Okay, mechanical velocity. Okay, so once the induced voltage, the current will start to fall, and at the same time the induced voltage will be increased. Current is reducing. Initially the current is very high, then it will reduce, and the machine start to induce voltage inside the wire loop. So the induced voltage will increase until sometime the machine achieve its steady state velocity. Okay, steady state condition, where at that time the torque is equals to 0. Okay, no more torque, because induced voltage is there, so no more torque, and the torque equals to 0, and at that time VB equals to E in. Okay, so we have this particular, let's say I have this current will be flowing and then reduce. Okay, at the same time the induced voltage will be increased and steady. So until sometime the current will be 0. Okay, current will be 0. So at that time we know that at this equilibrium or steady state condition, VB equals to E in. Okay, at that particular instant this machine achieve its steady state condition, which is VB equals to induced voltage. Okay, now we go to question B. Okay, what is the machine's maximum starting current? And then what is its steady state angular velocity at no load? Okay, so for B, the question is, what is the machine maximum starting current? Okay, B1, machine maximum starting current. Alright, so machine maximum starting current, we can just, at the instant of switch is on, okay, there will be no induced voltage. So meaning that we can just calculate the instantaneous current at that time as VB divided by R. Okay, which is 120 volt divided by 0.3 ohms. So we get 400 amperes of high current initially being drawn by the machine. All right, so that is B1. B2, the question of B2, let me just use another page. B2, what is the steady state angular velocity at no load? B2, steady state angular velocity at no load. So at the instant our switch is on, the initial torque was 0. Okay, so we can say that torque induced at that time is still 0.
Here are the top search results.
That means current is also 0. So okay, when it achieves the steady state condition, as has been described here, when it achieves the steady state condition, the torque will be 0. And current also will be 0 at that instant. VB equals to E in. Okay, in that instant VB equals to E in. Let's say I'm just write it down here. Torque is 0, therefore I is also 0, and then VB equals to E in. Okay, so VB equals to E in equals to, as from the formula, 2 over pi phi omega. Alright, so here omega mechanical is also omega electrical. This is mechanical, this is electrical, this is the same. So omega is VB 2 over pi phi, right? We can rearrange this sort of equation, and then we know that since phi equals to BA, so we can substitute phi equals to BA there. Alright, like that. And then we know that since AP equals to pi RL, then we can also substitute A now. So rewrite this equation. Omega is VB 2 over pi. We substitute A as pi RL. Now we can cancel pi. What is left here is VB divided by 2BRL. So we get omega is VB divided by 2BRL. Then we can just substitute the values. 120 for VB, 2B is 0.5, R is 1, L is 0.25. Right? Let's just confirm. B 0.25, R is 0.5, L is 1, VB is 120. Okay, so then from here we have already calculated the omega, which is angular speed, which is the steady state angular velocity. When this machine, DC machine, achieve its steady state condition, 120 divided by 2, 0.51, 0.25, we get omega equals to 480 radian per second. Okay, so that is the answer for B. Okay, C. Suppose a load is attached to the loop and the resulting load torque is 10 Newton meter. What would be the new steady state speed B? Okay, now what happened to this machine is this machine is initially we connect this battery and then switch on, and then what happen is current will be flowing and there'll be torque, and then this machine is rotates. This machine is rotating until it achieves its steady state condition. So once it is at the steady state condition, I connect the load. Okay, I connect the load, meaning that at that instant when I connect the load, the speed will be a bit reduced. All right, so that is the thing we want to understand from the third question. So we have the load of 10 newton meter connected to the shaft. All right, let's say, let me just redraw this particular illustrate this sort of third question. So we have this particular machine. All right, rotate at omega. All right, this machine rotate at omega, and after some instant I connect the 10 newton meter load. So when I connect the 10 newton meter load, what happened is this omega will be reduced. This omega will be reduced because of the opposite torque of the load. Because of the opposite torque of the load, this omega will be reduced. Okay, now we want to find in C, find the new steady state. When T load, tau load is 10 newton meter. I'm going to solve this at in the next page. So we can see that when the load is attached to the shaft, the machine will slow down, meaning that omega will be reduced. So we can say that omega is now, we can say that the induced voltage which is 2 over pi phi omega in this case. So the induced voltage, since the omega is decreasing, the induced voltage also will be decreasing, and at the same time current is now increased. Current is now increased. So when current increase, okay, the torque induced also increase until tau in equals to tau load. That is the story behind it. Okay, then this tau load is at lower speed actually. So speed. So we can say that it achieved the new steady state speed. Okay, it achieved the new steady state speed, which is tau load goes to tau in. Alright, so we can I simply represent this using absolute value, because actually let me just use the red color. I'm using the absolute value of torque. Okay, because at this time we don't know the condition now. is it the same direction or in the reverse direction? So that's why I'm using that absolute value of torque induced. But we know that the torque of the load torque is now the same as the torque induced. Okay, so you can rewrite it like this. Tau load equals to tau induced equals to 2 over pi phi I. Okay, in this case, we want to find the new steady state speed, right? So, okay, let me rearrange this to current. So, tau in is 2 over pi phi, and then since phi is BA, we can just substitute phi equals to BA in this equation. And then again, since AP is pi RL, I think the same thing what we have done in our previous equation, in our previous question as well. 2 over pi B pi RL. So in that case, we know that this pi can be cancelled. Okay, the rest, we have this equation becomes tau induced. I think I should rewrite in next page. So tau induced I equals to tau induced to tau induced divided by 2 BRL. Okay, so therefore we can substitute all of the values that we have. The torque induced, which is torque induced now equals to the torque applied, the torque of the load, which is 10 Newton. Then again, substitute all of the values that we have until we get the answer. So current is now 40 amps. So we have just determined the current. In this case, okay, in this particular case, we know that this machine, if this machine is working as a motor, meaning that VB is larger than induced voltage. Right? So, in our previous discussion in AC machinery, or we can, okay, we have just discussed about this situation, whether the machine is working as a motor or generator. It depends on the VB or induced voltage. So if the case of VB is larger than induced voltage, meaning that the machine is working as a motor. So we can apply the KVL, Kirchhoff voltage law. We can apply KVL, Kirchhoff voltage law. So you know that in this situation, VB is larger than induced voltage. So we can use this equation, VB minus IR, because in that case VB is larger than induced voltage. Now we know the VB is 120, and then we know the current, which is 40. We just calculate the current, and then R is 0.3. Okay, so we get here is, I think here is 12. 120 minus 12 is 108 volt for the induced voltage. That is for the induced voltage. The question wants us to find the new steady state speed. Okay, so once we get the induced voltage, it's easy for us to find the steady state speed using omega. Okay, now from there we have the induced voltage, we have the current. Now finally find the speed of the shaft lah, which is, this is the situation under load. Under load condition, we can just find the new steady state speed, which is omega is E in over 2 over pi phi. Okay, from E in equals to 2 over pi phi omega, right? We can rearrange this equation to omega equals to E in divided by 2 over pi phi. Alright, and then we can substitute phi as BA. We can use the same method that we have done before. Okay, we replace this phi with BAP, right? Then we replace this BAP as AP. We can substitute by pi RL, and then we can cancel pi, and then what happened next is so I'm not going to do it again. Okay, I've done this before, right? So basically we can end up this equation to E in equals to E in divided by 2 RL B, right? So we can just substitute the values. (432 radian per second). This is the new steady state speed after we attach the load. Okay. How much power? So there is still some other question that we need to solve in C. How much power is supplied to the shaft of the machine? So now in C3, let me just recap this. C1, this is C1. This is C1. Now we are moving to C3. C2. I'm going to calculate C2. So we have found the answer for C1, which is new steady state speed, right? Now I'm moving to C2, power supplied to the shaft of the machine. Okay, C2, which is going to write again, find power supplied to the machine, to the shaft, right? Shaft of the machine. Okay, so we can use the formula of P equals to tau omega, right? So we know that torque is 10 Newton meter, and omega under load condition just now in C1 we have determined the omega is 432. Okay, so omega is 432. Then power now is 4320 watt. So this is power that is supplied to the shaft. And then how much power being supplied by the battery? Okay, power supplied to the battery will, let's say this is C3 lah. Fine. Let me just rewrite again the question. Power. Find power supplied by the battery. So power supplied by the battery, P is VBI. Okay, we know that VB is 120 and current being supplied was 400 amps. So we have 4800 watt of power being supplied by the battery. This is the power supplied by the battery, and this is power supplied to the shaft. All right. You see that the power is supplied to the shaft is much more lower than the power supplied to the battery because supplied by the battery because this machine is working as a motor. That means the answer for this one. Okay, let me just solve this first. Okay, so meaning that in this case we have the power supplied by the battery 4800 and power supplied to the shaft is 43.200 or 4320 watt. Okay, this question doesn't ask us to find the efficiency. This is just to the next question is what is the machine working condition, which is the machine is working as a motor or generator. We can determine. Okay, okay, for C4 machine is working as a motor or generator. Okay, machine is working as a motor or generator. Okay, we can say that if VB is larger than induced voltage, this is motor. But if E in larger than VB, then this machine is working as a generator. So in this particular example, we have found that this particular example, this system that VB is larger than E in, that means that it is working as a motor. And then the direction of motion of the shaft is counterclockwise direction. All right. We still have some question. All right. Now, suppose that the machine is again unloaded. The machine is unloaded and torque of, let's say, let me just draft. Let me just let's say let me just make this question to a new page, which is D. Machine is now unloaded and torque of 7.5 Newton meter is applied to the shaft in the direction of rotation. Okay, just now we have motor and then it rotates at steady state condition, then we apply load and then the steady state speed reduce. Then now what happened is we detach or we unload that particular 10 Newton meter of load. Okay, and then we apply torque to the same direction of the rotation of the machine, meaning that we can imagine that this what is we are doing now is we want to make this machine, we want to turn this machine to the generator. Okay, so that torque is 7.5 Newton meter. So now we want to find the new steady state speed of the machine. Okay. Okay, so let me just rewrite. This machine is unloaded and torque of 7.5 Newton meter being applied to the shaft in the direction of rotation. Which is in the counterclockwise direction. Now we want to find the new steady state condition for D1 find new steady state speed omega. So the illustration is like this. We have this machine, okay, the shaft, all right. So initially this machine is turning to the counterclockwise direction with omega m. Then we apply the load of 7.5 Newton, purple, right? We apply the load of 7.5 Newton, tau load, 7.5 Newton meter to the same direction of rotation, to the counterclockwise direction. Okay, CCW as well. So in this particular instance, when we apply the tau load to the same direction, okay, we can say that when tau load in the same direction of omega m is applied, the rotor will
Here's some
accelerate.
information about Dorota-Kishlovsky. Countess Dorota-Kishlovsky is a recurring character in the Gossip Girl television adaptation.
Those current flows into the battery, okay? Current flows into the battery, meaning that the battery is absorbing power. You can just draw the situation now. What happened is the current is into the battery. That is the current. So in that case, E in is larger than VB. This machine is working as a generator. So now this machine is working as the generator. We know that. So it will produce reverse current, meaning that we can say that this reverse current will induce torque to the opposite direction, which is clockwise direction. So this reverse current will produce torque in opposite direction, which is clockwise direction. Okay, so the induced torque opposed to the external torque, external applied torque, and eventually, okay, the load, tau load equals to tau in, okay, at higher omega m. Okay, we can say that the induced torque oppose the external applied torque, and finally and eventually tau load. Again, I use the absolute value. Tau load equals to tau in at higher omega m. Alright, that's it. And then at this particular instant, the current in the rotor will be, so the current in the rotor will be I is tau in divided by 2 over pi phi. So we have seen this sort of equation. All right, we have seen this sort of equation. It is from torque induced equals to 2 over pi I phi, right? So we can rearrange this equation to find the current like that. So now torque induced divided by, so we can do the same thing for this phi. All right, we can do the same thing to further substitute the value of the phi here. Then finally we get torque induced is 2 over, so we have cancelled already pi, so torque induced divided by 2 RLB, the current. Then we can just substitute all of the values that has been given. The torque is 7.5 divided by 2 times 0.5, R is 0.5, L is 1, and B is 0.25, and then we get 30 amps for the current. So then the induced voltage, so we know that this machine is now working as a generator. The induced voltage is now larger than VB. All right, the induced voltage is now larger than VB, so we can use the formula using Kirchhoff voltage law. Induced voltage is equals to VB plus IR. Then we can calculate the induced voltage now. I is 30 amps, R is 0.3. Now we get the induced voltage of 129 volt. And then in this particular question, in this question D, the first question is to determine whether the to determine the new steady state speed, right? So we have already found the induced voltage, which is 129 volt, and then finally we want to find the speed, right? The speed of the shaft we can use this particular equation. Omega is E into over pi phi, and then further we calculate this which is E in divided by 2 RLB. So we can use that equation, which is omega E in, we know that 129. Then just substitute all of the values. All right, and then finally we get 516 radian per second with new steady state speed, which is much more greater or larger than the initial steady state speed. Okay, and in D2 the question asks us to determine whether this machine is working as a motor or a generator. Simply we know that this machine is now working as a generator. This machine is now working as a generator because VB is because induced voltage is larger than VB. Okay, E, suppose the machine is running unloaded. What would the final steady state speed of the rotor be if the flux density were reduced to 0.2 Tesla? Okay, in this particular question, the flux is now reduced to 0.2 Tesla. Okay, let me just rewrite the question. If machine is running unloaded, what would be the final steady state of the rotor if the magnetic flux density reduce DUCED to 0.2 Tesla. Initially it was 0.25 Tesla, right? In the question, the flux was B was 0.25. Now the B has been reduced, okay, to only 0.2, meaning that 0.05 Tesla of the flux has been reduced because of some of the problem related to commutation process, right? uh, Flux weakening, for example, that will makes the machine suddenly reduce its flux intensity. Okay, so for this particular case, okay, we know that the no load speed, no load, okay, speed was 480 radian per second, right? That was we have determined this before. The no load speed 480 radian per second. Where is it? Okay, here. The no load speed is 480 radian per second. So when flux reduce, okay, what happen is we can use the induced this equation. Let's say when the flux reduce, okay, we can use this equation to find the speed. All right, we can use this equation to find the speed. Okay, so omega and then we can further extend this. Meaning that after some situation, the induced voltage will be equals to VB. Okay, after some instant, we know that E in equals to VB when it achieves its steady state. Right? So we can use this equation, which is in this case we can substitute phi and then until we get omega equals to E in divided by 2 RLB, right? Where is it? Before this we have done this 2 RLB, yeah? Omega is E in divided by 2 RLB. So we get this omega is E in divided by 2 RLB, right? So at the steady state condition, E in equals to VB. So we can still use this, that we can substitute E in now to VB. Okay, all right. So we can substitute this E in with VB because after some time this machine is achieved the steady state condition, right? What would be the steady? Okay, final steady state speed. When this final steady state speed, I mean, it means that at the equilibrium or the steady state condition here, the steady state condition here, okay, we can just replace this with VB. All right. So let me just use black color again. So we can just substitute the values. So this gonna be, I'm using this B. This B is the new B, which is 0.2. Okay, this is the new B. Okay, the new steady, sorry, the new flux density lah, 0.2 Tesla. Then the answer is 600 radian per second. So we can say that when the flux in the machine decrease, the speed increase. Okay, when the flux in the machine decrease, the speed increase. The speed increase. Okay, flux weakening, meaning that sometimes it happens when occurs flux weakening because of the problems with the commutation process. The speed will be increased. All right. Okay. So this is the same behavior of the linear DC machine. Okay, I think that's all of the that's all of the questions from A to E that has been discussed. I would like to finish this tutorial up to this time. Okay, so that's all. Thank you.